Uh, Good afternoon or good night. I'm not sure about. It depends where you are. But regardless, it's a pleasure to share this tutorial. We are in the I'm Sydney, and we are on the second day of the SBMF, but we've considered the ETMF, the first event, the school. We are in the third day of events. Good discussions, good talks, good lectures. And now we are in the second tutorial of the SBMF. And this tutorial will be presented by Alvaro Miyazawa. He's a lecturer of the Department of Computer Science at the University of York. He worked with software engineering at the University of for Robotics group. Yeah, he main research has been for semantics and refinement for domain-specific language, also graphical notations to develop refinement strategies, support high level of automation and program verification. And currently, his research focus on modeling, simulation, testing, and verification of robotic systems. And so this is why his tutorial is RoboStar and RoboTool, software engineering for robotics using formal methods. Okay, so it's a pleasure to introduce you, Alvaro, and the word is with you.
Thank you for the introduction. I'll just start sharing the screen just a second. Okay, everything's working. Everyone can hear me. Okay,
it's fine.
Okay, cool. Yeah, so yes, my name is Alvaro, and I'm a lecturer at the University of York in the UK. And what I'll be talking about is the work that we've been doing in our group that we call RoboStar, which is the software engineering for robotics group, and also a tool that we have developed here to support the work that we're doing within the group. And I just wanted to mention also that the group expands beyond the University of York. We're working with people in Brazil, in Europe, in China, all over the world. So this is not all my work, it's a work of all of the collaborators. Okay. So while talking to roboticists, both in academia and industry, one thing that a pattern that we noticed was that they would often start with what we're calling an abstract model, but that wasn't called an abstract model. And these models were usually hand-drawn state machines. We have even like some evidence that people would use these drawings, put them all in a table, and then start hunting for deadlocks on paper. And once these state machines were drawn, they were often implemented by hand again into controller code that would be used in a second phase for simulation, where the controller code would be based on those state machines, and a simulator would provide the execution of the hardware and of the environment. So the connection between the state machine and the controller code is usually informal. And once the simulation is accepted as adequate, the controller code would be rewritten completely or adapted to work on a real robot. So this would often involve changes to API calls, or even changes to parameters of the controller so that it works when you have the imprecision of the real world. Now, one problem here is that any bugs that were found during the second or third phase would have been corrected at that level. So if during simulation a bug was identified in the controller, it would usually be fixed at the controller and nobody would bother going back to to the drawings to redraw or fix the state machine. And similarly, if the bug is found at the implementation level, the simulation or the state machines would not be corrected. So that means that everything that was done before is in a way lost. Now, the approach that our group is proposing is based on domain-specific models for robotics, and it starts with two languages that we're calling RoboChart and RoboWorld. And we'll talk a little bit more about what these languages are. But the idea here is that from these models, which should be convenient for roboticists, not just software engineers and formalists, we would be able to automatically generate proof models that would then be fed into model checkers and theorem provers to evaluate their correctness with respect to properties and specifications. Now, if we observed that the models were not valid, the idea is that we would go back, adjust the RoboChart and RoboWorld models, and then run everything up to that first decision point automatically. So there wouldn't be extra work to be done just fixing the bug. If, on the other hand, we decide that the models are valid, we would automatically generate something that we're calling a RoboSim model, which is a model tailored for simulation. And again, I'll talk a little bit more about it. I'll demonstrate the tool around RoboSim and RoboChart. We could also, from RoboChart and RoboWorld, derive test cases. Now, there would be multiple approaches to doing that. They could be done manually, but could also be done automatically. And based on the RoboSim model and the test cases that could be generated, we would run the simulation in some robotic simulator like Gazebo or Copilot Sim. Now, based on those tests, if we decide that the model has a problem that's not valid, we can again go back to the RoboChart RoboWorld model, fix the bug, and again automatically rerun everything up to the point where we stopped until we get that we're satisfied with the simulation. In which case we can again automatically generate deployment code. And in this case, we would take the test cases that we obtained before and convert them into test cases that can be run on a real robot. So that might involve generating configurations for the robot, but also telling people how to set up the environment where the test would run. And based on the converted test cases and the deployment code, we would run a test on the real robot. And again, if we find a problem, a bug, we would go back to the RoboChart RoboWorld model and rerun everything automatically until we're happy that all the tests have passed. And at that point, we would have a collection of evidence of the correctness of the system, or kind of that to give you confidence on the system. So that would be the code that's been generated, all the proofs, test results and assumptions, and also any environment restrictions that have been identified. Now, to support this approach, we're developing a framework that's centered around those languages that I mentioned. So at the top level, we have RoboChart and RoboWorld. RoboChart is a notation similar to UML based on state machines, slightly more controlled than UML with a formal semantics, where a controller is described in terms of services that a robot might provide. And these are described in terms of variables, events, and operations. So, for example, a robot might have an obstacle sensor that would be described in terms of an input event called obstacle. And at the same time, it might be providing operations like move, which would tell the robot the speed of the wheels or the speed that the robot should have overall. RoboWorld, on the other hand, is a controlled natural language for specification of operational requirements. And the idea here is that the RoboWorld is saying under what conditions a RoboChart controller should behave correctly. At that level, what we have really in RoboChart is a reactive model where if the controller is prepared to deal with an event happens, it will deal with that event. And on the RoboWorld model, it's more of a hybrid model where you have continuous and discrete behavior. In the next step, we would drop into the simulation phase, which is where that other language enters, RoboSim. And here, we break this language into three different models. What we're calling a D model, which is equivalent to the RoboChart model, except that here there's an explicit notion of cycle, and you have restrictions of when you can read events and when operations can be executed. So it's a cyclic model. We have something that we're calling a P model, which is a physical model, the model of the robot. And this model is hybrid. It has both continuous and discrete behaviors. And then we have the S model, which is the scenario model, which again is hybrid. The idea here is that the D model corresponds to RoboChart, and the P model and S model are concrete versions, in a sense, of the RoboWorld description. The next step is to figure out how we can make these different models talk to each other, the D, P, and S models. And to do that, we're using something we're calling platform mapping. And these are relating the inputs and outputs of these different models. So in particular, in the case of the D models, we're relating the inputs of the D model, so for example, the obstacle, to the output of a sensor in the P model, of the obstacle sensor. And similarly, we're relating the output of the D model, like an operation move, to apply specific voltages at the actuators, at the motors of the P model. And again, similarly, in the interface between P model and S model, we would translate, for example, outputs of actuators into the effects of those actuators on the world, and the effect of the world on sensors are translated as inputs to the sensors. At this point, we have a somewhat complete model of the system. We have the environment, we have the robot, we have the software, and we can start up using different tools to analyze the thing. So some of the tools that we've been using to analyze all or parts of a RoboSync model are these. So we have Prism and FDR4, which are model checkers. Flowstar and Cora are hybrid model checkers. Drake, Copilio Sim, and Gazebo are simulators, and Isabelle UTP is a theorem prover. I'll show a little bit of what we can do currently and what we've been doing right now with all of these tools and languages. So just a bit of information, RoboChart and RoboSim. If you're curious about the notation, there's plenty of documentation on the website, the first link. There are reference manuals describing the syntax, meta model, well-formed conditions, and the semantics of these languages. There are a number of case studies on our webpage as well, and I'll base today's tutorial on one of them. You can look for more details and download the models from our website. And also there are a few key publications here. The first one is on RoboChart. The second one is on RoboSim. And the third one is on the probabilistic aspects of RoboChart. And then finally, RoboTool, which is an Eclipse-based tool that was developed to support the work that we've been doing. So it's developed using Xtext and Sirius, which are frameworks for describing textual and graphical notations, and also a tool called Epsilon that was developed in York, and it's a framework for model-to-model transformations and other kinds of transformations. If you want more information about RoboTool, you can find in the website. There are tool manuals. There are a couple of tutorials there as well that you can follow. And if you want to download the tool, you can use this update site here, or downloads the tool with all of the plugins that I'm using already from this other URL here. But we have very strict requirements for RoboTool right now. So we're asking people to use Ubuntu, Java 11, Eclipse 2021-12, and FDR4 and Prism. And the main reason for this restriction is that we're supporting use of RoboTool in these platforms, and we don't really have the resources to support all of the other platforms. So if people want to use on Windows or Mac, they can try, but we can't really help with any platform-specific bugs. On the optionality of FDR4 and Prism is if you want to be able to analyze the models, you need one of these tools, depending on the kind of analysis you want to perform. Okay, so the example I'm using here is the SRanger. There is a web page on our website describing this example, showing all of the models and the results that we have been able to derive. And the steps I'm going to go through is first modeling this example with RoboChart, specifying assertions with a RoboCert, which is our assertion language, verifying RoboChart models using both FDR and Prism, creating simulation models using RoboSim, then verifying these same models. I'll then briefly show some of the physical models that we can specify in RoboSim, and then discuss some of the latest developments, which are generation of code for simulations, the verification of the composition of the P models and D models, the hybrid and discrete models, and also a little bit on automated testing, if we have time. So I'll start with a RoboChart model, but I'll start creating in the tool here. So this is Eclipse with RoboTool installed. There are a number of buttons here at the top that allow you to access some of our code generators. If you decide to install, one of the things that we need to do here is in the preferences, you need to select RoboChart analysis and then give the folder where FDR is installed. And similarly for RoboSim, yeah. So there are some configurations that we need to give to RoboTool so that it can run automatically. So I'll start creating the RoboChart model by creating first a RoboChart project that I'll call SimFW. And here I'll create a RoboChart package. I'll call it SimFW again. Okay, cool. So now we need to start thinking about first what kind of robot we want to model for, and also what the controller should do. So the controller that I'm thinking here is a very simple controller that starts moving forward. If it finds an obstacle, it turns 180 degrees and then goes back and continues doing whatever it's doing. To do that, we need a robotic platform that allows us to move the robot somehow and also detect obstacles. So I'll describe two interfaces that provide these services. So I'll call it movement I and obstacle I. Within movement I, I'll specify two operations. One, move, that takes a linear speed and an angular speed. And another operation that I'll call stop. Doesn't take any parameters. And on the obstacle interface, I'll define an event obstacle that doesn't really give any more information, but it could in principle produce some value. So at that point, we can start modeling the system as a module. Let's call it C movement. And this is like a main procedure of RoboChart. It's the main point of the system. And a module needs to have a robotic platform. Let's call it SRanger, which will describe the services that can be used. So in particular, it will define, this interface obstacle I. So it will say that it has an event obstacle on which it can, other controllers can interact with. And it will also provide the operations in movement I, because these are operations of the hardware. Then we need to define a controller. So right in this example, we only have one controller, but you could have multiple controllers running in parallel. We'll call it movement. And again, it needs to define this interface obstacle. And now it needs to require the movement I interface so that whatever is inside the controller can use those operations. Then we can connect the obstacle from the platform to the controller because it's an input event, and it's an asynchronous communication because it's any communication between the controller and platform is considered synchronous here. Now we can start building the state machine. So I'll build it separately here, and I'll call it S movement. And you can see that there are already a few errors here at the bottom. One is saying that we need to have an initial state, and one is saying that there must be at least one state machine in controller. So we'll slowly fix all of these errors. So we can start by creating an initial junction here, and we need 2 states in the state machine. So I'll specify the state machine so that it starts moving until it sees an obstacle when it starts turning. I'll connect the transitions, and that should solve some of the errors. Let's see. Yeah, one of the errors disappeared. And then, as I said, I want, as soon as I get into moving, I want to start moving the robot. So I'll create an action that needs to be an entry action, an action that's executed as soon as the state is entered. And this action will call the operation move with some value for the linear speed and 0 for the angular speed. Sorry, I forgot to add the required operations here. So I need to require that interface before I can use it. And while I'm here, I'll define the obstacle event. Okay. So now I should be able to put my entry action here. Yep. Now, if I'm moving forward and I find an obstacle, I'll take this transition. So if I find an obstacle, I want to stop the robot and then start turning, which is what I'll do next here. So I'll do entry, move. This time the linear speed is 0, and I'll say that the angular speed is 1. And then once I'm done turning, I can go back into moving forward. Now, a problem here is that this transition that doesn't have any guards or events will be taken as soon as it can. So as soon as it starts turning, it will move into the state moving. So we need to do something here to control how soon this transition can be taken. And to do that, we need to use information about time. So we define a clock called MBC. And I'll also define here some constants to make my life a little bit easier. I'll call LV, which is real number, AV, real, and I'll also define pi as a real number. So now I can use this clock to control for how long I should be turning. So what we'll do here is first I'll replace that 1 by the constant so that I can easily change those values. And I need to start counting from the time the robot stops to until some time after it starts turning. So to do that, I'll have to reset that clock. Initially, it will be 0, but eventually it will not be 0. So I'll reset the clock by putting this operation here. So that's resetting the clock MBC. So at this stage, as soon as the transition is taking, MBC is equal to 0. And then I'll get into turning. I'll call move. But now I don't want to move immediately. I want to wait a little bit before I move into the other state. So I'll put a condition here between square brackets that says that the time that has passed, that has been recorded in the MBC clocks, is greater than or equal to pi radians divided by the angular speed. So once enough time has passed that we've turned 180 degrees, that at that point, we can go back into the moving state. There's one more thing that we need to do here to make sure that the things work as desired, which is saying that some time needs to pass after you send the message so that at least the movement can start. So we're saying here that we're waiting for one time unit after each of the operations. And this will be important later to make sure that this state machine can be scheduled into a cyclic simulation. Okay, so now we have our state machine. We still have an error there because it's missing a state machine here, so we can use a reference here and then just connect the events. Now we have a model, a complete RoboChart model. There's one warning here about timed expressions like this, and this is because we provide two versions of the semantics, one with time and the other without time, because time could make things difficult for the model checker. But if you're not using the timed semantics, then you need to be aware that conditions like this are ignored. So that's how we construct a RoboChart model. I'll close this project now and open a similar one with a few more things here. So we have our RoboChart model here. It's the same that I've created before. And at this point, we can start asking ourselves questions about the model. So we could ask whether the module here, C movement, is deadlock free, whether it's deterministic, whether it refines a particular specification. And we can do that using this file here, simfw assertions. There are a few details here, which is that the constants that we hadn't defined before need to be specified here. So you can specify them in this file. And we're saying, for example, that the linear speed is 1 and the angular speed is always 2. We also have here a simplified specification of the behavior of the system so that we can check that the actual model corresponds to this simplified specification. And we can also check properties like this. So here we're checking that the controller that we just designed is equivalent to the specification that I had, and also that it's deadlock free and it's deterministic. So if I have a file like this assertion file, I can then go up here on the little person running, and that should call FDR in the background and produce a report relating the results that FDR provides and the assertions that we had defined before. So we can see here that the model we designed is equivalent to our specification, and also that they're both deadlock free and deterministic. So now that we have a model in RoboChart, we can start thinking about a simulation of these RoboChart models, a cyclic simulation. So to do that, we use that other language that I mentioned, which is RoboSim. So I'm not going to draw the diagram because we don't have that much time, but it's similar to what we had before. The construction is similar. And here the main difference is really that all of these components, the module, the controller, and the state machine, specify what a cycle is. So in this particular case, we're saying that a cycle is one time unit. And the state machine now is a little bit more detailed, because before we could talk about waiting for one time unit. Now we can only talk about waiting for the next cycle or for the next few cycles. And that's what this thing is doing here. So we're starting from the state as moving, where we ask the platform to move. The dollar sign here is indicating that this is a platform operation. And immediately after that, we go into this state demoving, where we wait for the next cycle. And this is what the exec event is doing here. At that point, we can look at what the value of the obstacle event was at the beginning of the cycle. If it's not true, we go back to the moving and wait again for the next cycle. If obstacle is true, then we do what we were doing before, which was resetting the clock and calling stop. Then again, we wait for one cycle, which is that wait one that we had before, and do the same thing for turning. We ask it to start turning, move into this state where we wait for the next cycle, see if enough time has passed. If it hasn't, we go back to the turning and wait for the next cycle again. Otherwise, if enough time has passed to turn 108 degrees, we go back to as moving and then continue everything again. So the same thing we've done before can be done for this RoboSim model. And this is specified in this file here. And again, we have a simple specification of the system that we can compare to the controller that we have just created. And we can also check the properties like deadlock freedom and determinism. So I'll use a slightly different way of checking this, which is opening the semantics directly into FDR. So we would take this C movement assertions file here, open with FDR, and that will open the file in FDR. We can run it all, and it will check all of the assertions, and all of them passed. So all of those properties hold. Now, a more interesting thing that can be checked here is whether this new RoboSim model that we created is equivalent in some sense to the RoboChart model. They're not directly equivalent because the RoboSim model has further restrictions on the order of interactions with the environment. But we can define a simulation based on the original RoboChart model and then compare this simulation to the RoboSim model. So that's what we're doing here. We're saying that the RoboChart model, we can use it to build a simulation automatically with a cycle of size 1. And then we can compare these the RoboSim and this simulation. But what we want is that the RoboSim model refines the simulation based on the RoboChart model, so it could resolve non-determinism, for example. So we can perform this check here automatically, and I'll run it again here. So if I open it with FDR, we can run all of the assertions. This takes slightly more time, but again, it passes. So the RoboSim model is equivalent to the RoboChart model with the specific notion of equivalence that we have for RoboSim. And you can find more details of that on the second paper that I mentioned on my slides. Sorry. Okay. So I'll take a detour here just to go back to RoboChart and talk a little bit about probabilistic modeling in RoboChart. It's a simpler example than what we have for the SRanger, but if you want to look at what was done for the SRanger, you can look at the case study. The case study webpage, and there's a larger model there. So here we have a very simple module with, again, a single controller and a robotic platform offering only events. So in this case, it's an input event flip and two output events forage and stop. The controller has a single state machine, and all it does is, while in the forage state, it keeps receiving flip events, and if the count of flips is not yet n, it can take this junction here, which is a probabilistic junction indicated by the p, where it will take one of the transitions based on the probability that's defined here in the label. So with probability half, it goes back to forage, otherwise it goes to stop. In either case, it will increment the flips count up to n, but in the first case, it will produce an output event forage, and in the second case, it will produce an output event stop. Now, the idea here is similar to what we had before. We can specify assertions over these probabilistic models. And this time, we can't use FDR. We need to use a different model checker, which in this case will be Prism. So in these assertions, we're saying that we can define the constants that our model use to take certain values. So in particular, we're saying that n should be taken from the set of natural numbers from 2 to 20, kind of taking steps of size 2. And then we can specify properties of the system. So we could say here that we can check that that module is deadlock free. And that would be equivalent to say that there's no path where you finally reach a deadlock. We can also check for non-termination. So in all possible paths, we reach that state stop. And then we can also ask questions about the probability of some of these things happening. So the minimum probability of terminating, the maximum probability of terminating. And then finally, we can also define rewards for some of the events. For example, here we're saying that if an input event flip happens, we get a reward of 1. And then we can use this reward to calculate some values about the system. So the minimum number of flips for reaching the state stop, and the maximum with kind of different types of constants. And again, we can take this assertion file and run it on Prism. So in this case, we would go here to RoboTool, Prism, run, and it will run in the background. So if you see here, it's running and produce a similar report. In this case, because we said the constants could be any value within the set, it's producing one assertion for each possible value. And in this case, it's showing that it is deadlock free, but it doesn't necessarily terminate. So we can look at the probability of terminating. The minimum probability is 0, and the maximum probability starts increasing as the constant n increases. And then similarly, we can calculate information about the rewards. In this case, in both cases, the value that we calculated is infinity. So that's what can be done with Prism for now. So I focused so far on the software bit, and the more recent work that we've been doing is on modeling the hardware, the P model, and also the environment S model. So I'll show quickly here what the P models look like. And they're inspired by a notation called SDF that's used as an input for Gazebo, but with some extra modeling constructs. So here we have a P model of the robot, of the SRanger, that's parameterized by the size of the robot itself and of the wheel, and also by the constant pi, which is defined here. And then we can start describing this robot, the P model, in terms of links, bodies, which are rigid bodies, joints, sensors, and actuators. So in this particular case, we have a base link that has two bodies forming it, a chassis and a caster wheel. And we have two other links, which are the wheels of the robot, the left and right wheel, each of them defined by a body, which is a cylinder. Now, our base has a sensor that's positioned relative to the length and height of the base. And this sensor is defined as taking an input as a distance and producing as an output a voltage. And the relationship between the input and output is established by this equation here that was calculated based on experiments run on a specific type of sensor. The base also has two joints, the left and right joint hinge of type revolute. And in this case, the equations of the joint are specified based on rigid body mechanic equations, and they are all specified in a library. The only thing we need to provide here is the axis of revolution. And each of the joints also has an actuator, which is a motor, that in this case takes the desired angular speed and outputs the torque that the motor produces. And then finally, we need to link the output of the actuator to the input of the joint. So we're saying that whatever torque the motor's produced is transferred to the joint here. And this is given by this equation here. Now, at the moment, what we can do with these models is first generate the equivalent STF model so that we can input it into tools like CopiliaSim and Gazebo for simulation. But we can also produce a hybrid model that includes all of the information about the equations which are not available in STF and are implicit in the implementation of the simulators. We can keep all of these things and produce a model. Right now, we're producing it in a language called Sci-Fi Circus, which is a hybrid state-rich process algebra. And the support is for this language is under development based on Isabelle UTP, the theorem prover. So before I talk a little bit more about what can be done with this, I'll also mention show the platform mapping that I had discussed before. So this is the point where we say how we can interpret those abstract events and operations of the D model in terms of the inputs and outputs of the P model. So here we have the obstacle event, and we're saying that an obstacle happens if the output of the infrared sensor is greater than or equal to 3.0. We can also say the effect of an operation, for example. So stop here, the effect is to set the desired angular speed of the motors to 0. And a slightly more complicated example, the operation move uses these local variables to calculate what the speed of each of the wheels needs to be so that the linear and angular speed of the whole robot is as desired. So the platform mapping essentially connects the D model and the P model and produces a complete model of the robot. So based on that, we're working towards a few different directions with these languages that I've talked about. So the first one is based on code generation. And the idea here is that if you started from a RoboChart model, you could generate automatically a RoboSim model, this one here, and there's ongoing work on automating that generation. And the idea there's the model-to-model transformation from RoboChart to RoboSim guarantees correctness of the RoboSim model with respect to the RoboChart model. And then based on the RoboSim model that we produced, we could automatically generate some platform independent code. Right now, we're producing an intermediate representation that then can be easily translated into languages like C and Rust. Based on the platform mapping that I have just described, we can produce generators to implement wrappers for specific tools like Copilha, Sim, and Gazebo, and that basically translates, using information from the platform mapping, the events and operations that the platform-independent code uses in terms of the API of the simulators. As another direction that we're looking into is how we could use the equations that are embedded in the RoboSimP model to produce tailored simulations that used exactly the correct equations, or the equations that we want, to produce a simulation just for this, for the example. We're also looking into extending this to deal with testing. So we're looking into a tool called RT Tester, produced by a company in Germany called Verified Systems. And the idea here would be that we would also produce an RT Tester wrapper that would allow RT Tester to run and control the execution of our platform-independent code. A second direction of the work that we're doing is on analyzing these models that we have created. So there's more information on the case study page, but the work that has been done so far by a colleague of mine in New York is to take the model of the SRanger, use our semantics and our code generators to produce a TOC CSP semantics of the D model and a sci-fi circus semantics of the P model. These two are composed in parallel using information from the platform mapping to translate the information from one to the other. And then the composed model here is being fed into Isabelle UTP to prove properties about the whole system. And basically Isabelle UTP is producing conditions that need to be checked, and these are being checked using model checkers like Cora and FlowStar. The example we have is a simple property, like if an obstacle appears in a certain position, the robot will stop within a certain amount of time. But it was a proof of concept that showed that it's possible to use Isabelle and these hybrid model checkers to check properties of the whole system. Yeah, and I think that's all I have to say. If there are any questions, I'm happy to answer them. Thank you.
Thank you, Alvaro, for your tutorial talk. Many interesting things. In the original schedule, we only have 7 minutes, but because we waited 5 minutes to start, maybe we can have 5 minutes of extra time for questions if the organization agrees. Okay. So the audience have some question. Let me see. No, so far, but while maybe audience is elaborating, I have some questions. I can have an initial question. Is that you showed a lot of language that can and for different models that can be transformed in stepwise way. My question is, if somebody that is seeing the tutorial wants to use this framework, this tool, does it need to use everything, or is it possible to use only one kind of model? And if you use just one, you see it's possible to create a hobo scene instead of first creating a hobo chart. And if you do this, if you do something, or no problem, can you talk about that?
Yeah, you can use any of the languages that you want. So you could start from a RoboSim model, and then if you produce a RoboChart model, you could check that they're equivalent. You could just stay in the RoboChart model. So I have a student that will be looking into implementing RoboChart models directly into ROS without going through the cyclic component. So you could stay in any of the levels that you want. We're also, the idea here is really these languages are kind of prototype languages that facilitate the proof of concept of the approach that we're taking. So in principle, we could have had UML with some restrictions over the language, like a profile of UML. But the idea here was just that by specifying the language to be as restrictive as we wanted, we could easily give the semantics and produce a tool that generates the semantics. So the idea here is that we could even replace some of these languages by other notations. So in particular, when we have P models, if you want and you have a Simulink model, in principle, you could use the Simulink model there. So we have some work on we have done some work on integrating RoboChart with SysML, with Simulink. There's some ongoing work about testing models that are created in RoboChart and in Simulink, and using kind of different tools to produce tests. So yes, you can use any of the languages independently, and hopefully the hope here is that we could integrate with other notations, because the goal of the project was not to tell roboticists what they need to do, but or what languages they must learn, but to make whatever they are already doing more formal. So instead of teaching them how to use CSP, we're taking the state machines that they're already using and just making them formal.